So I would like to introduce our recent study about the machine learning in molecular spectroscopy. And we know that the spectroscopy is a useful and powerful tool. It can bridge theory, property, and structure. Actually, the building of quantum mechanics we know is based on the interpretation or understanding of atomic spectrum. We see that we extract information about the hydrogen atomic spectrum. We know that the atomic orbital model, and we deduce the Broglie wave, and so many key concepts in quantum mechanics. And now, as we know that we are moving forward from the atomic spectrum to complex system. Spectrum are widely used for many complicated systems and materials. Fortunately, they are still based on the known rules of quantum mechanics, but unfortunately, the extremely high complexities and of the chemical structure and also their physics properties variations led to huge difficulties to reveal the one-to-one correlationship between structure and the spectrum. So it is hard to interpret them from the theoretical point of view. So therefore, in our study, we are trying to rebuild or to establish the one-to-one relationship between structure and the spectrum. Here, we are trying to use artificial intelligence, machine learning, to accelerate or to reveal the unknown or to predict new rules from the data. Well, for one side, we try to do the spectroscopic prediction. That is to do the quick simulation for possible chemical structure. After that, we compare the simulated spectrum with experiments. That's one from the structure to spectrum. On the other hand, we realize it is might possible to do it in worse, to do the spectroscopy retrievement. For example, we try to use AI to integrate the spectrum to automatically reconstruct the chemical structure from the spectroscopic signal. This is going to be a very useful tool for us to understand the rules and also to reveal the unknown mechanism. So let me try to describe our recent results here. Firstly, we go from the traditional way to predict the structure, to predict the spectrum based on structure from quantum mechanics calculation. And we know this is a painful task. Therefore, we try to apply machine learning to accelerate this process. We are choosing the plotting as a study subject. This is because plotting, of course, are very important. And we know that they are also complicated. Normally, if you want to simulate their photo response, we need to construct their Hamiltonian matrix, which contains this Hamiltonian matrix element from the calculation of excitation energy and also the excitation couplings. While these couplings are not easy because they need us to do the integrals at the quantum mechanics level. This, as we all know, are the bottleneck problems of quantum chemistry study. To make it worse, we know that the structure are not fixed. They're always moving, and also they have this evolving all the time. Therefore, normally we need to have like thousands or even millions of molecular dynamic snapshots to get the configurations. Then, based on that, we do the quantum mechanics calculation. This just become mission impossible. Nobody can afford. That's the huge computation costs. Therefore, we can apply machine learning to accelerate this step. The protocol is quite straightforward. First, we prepare a database. We prepare the data for the structure parameters like coordinates, the bonding lengths, the angles, and so on. After that, we extract the descriptors. We do the quantum chemistry calculation. Then we should have this data of Hamiltonian because we do it strictly. After that, we have a data set which correlates the structure with the Hamiltonian or with the photo response signal. Then we can run the machine learning like the neural network, the standard neural network to build the model to correlate the to build a quantitative correlation. As we know that machine learning is quite good in transferability. Therefore, out of that, we can input the descriptors of any other new protein structure. Then this model will be able to give us the Hamiltonian matrix at the first principle level. This will enable us to predict the spectrum. But doing that, we can now remove the database. Yeah, we don't need to go back to the painful quantum chemistry calculation anymore. So let me try to show our results. Yeah, here is the network we are building to model the relationship between structure and the photoresponse signal. Yeah, we take 100,000 peptide bonds as the data sets, and we prepare their quantum mechanics information as a training set. After that, we can get, for example, we can use the model to predict the dipole moment, electrical dipole moment for 20 types of amino acids, and also for their peptide bonds. Yeah, this will help us to build the basic units for any protein. For example, we now can input the structure of a real protein, and then this neural network model will help us to predict their photoresponse almost immediately. You see, we have worked on this ultraviolet signal and also the infrared signal. Infrared signal I like the most because infrared they provide the local signal, which help us to identify the local details. So for here, we can see we tested with various protein structure. They contain alpha second structure, beta second structure, and so on. And normally we can use ML to accelerate the calculation for like 5 magnitudes of speeds. Of course, we get a good agreement with the hard calculations. Yeah, and we can also use it to compare with experiments. Here we try to predict the spectrum for this small protein, ubiquitous protein, and we try to apply it to the data set at a different temperature, 1.63 degree or to 80 degree, and we see the agreement between the ML predicted results with experiments are quite good, and we actually can follow their relationship. Yeah, and also we can follow the evolution for treatment of cage during the folding process. This could be very useful now because we know that sometimes people want to know how the protein are folded to do in a 3-dimensional structure. But then with spectroscopic signal, we're able to monitor their process. So we actually have now built a website where people can input their PDB structure, and then we can produce the UV, Raman, and the C circular dichroism spectrum in very quick speeds. And recently we have tried to apply this model to study this ConV19 virus to see how it interacts with the whole human protein. Yeah, then we see that the signal, because we can do it quickly, therefore we are able to produce the evolution of the infrared signal. And from the evolution of the signal, we see how their structure are changing. For example, we change from alpha helix, and then we have more beta turns, second structure. Yeah. Then we propose that this could be a powerful tool to do biological monitoring. But after I present it in paper, and the experimentalists start to doubt me, challenge me, because they said, if you already have the structure, why bother to produce the spectrum? Yeah, because you have all the structure coordinates. You can just tell people directly what is the beta, how many beta structures are in your protein. Yeah, I got the how to say challenged by this question. Then we started to say maybe it is more important to do it in worse if we are able to extract the information, extract the structure detail information from the spectrum, but even mostly importantly from the experimental spectrum. Then it will help people to understand how the protein are evolving during some important interactions. Yeah, that's why we are now focused on the retrieve process to try to integrate the complicated spectrum with the help of machine learning. Yeah, we have to rely on machine learning. Although in principle, the spectrum should contain all of the information, because as we see, Newton already said a long time ago, to understand structure, you only need to see their spectrum. But we know that the measuring of a spectrum is actually a way of losing information, because you are reducing the dimensionality of the real world. For example, we have a 3-dimensional structure here. If we shine light, we can record a so-called spectrum on this wall. And we see that we have a 2-dimensional spectrum. And here we have another 2-dimensional spectrum. With this 2-dimensional spectrum, it is actually impossible to reconstruct the real structure back. Yeah, because we are in lack of information. How to get the reduced or the losing information back? I think the answer is from the database. If we can prepare a database which contains a lot of correlation between various protein and various spectrum, then we are able to use this machine learning techniques with the help of these good descriptors to retrieve the one-to-one correlation between spectrum and structure. With a quantitative correlation, we may be able to infer the real structure from some spectroscopic signals. Yeah. Of course, we are just starting to do that. We don't have fancy results yet, but we believe that this is a good direction. For example, here, we are trying to do it firstly to recognize the chemical groups. We know chemical space are consisted of different chemical bonds, different chemical groups. So we started with like this carbonyl and also this hydroxyl the groups OH and CO. And then we prepare data sets for like 20,000 molecules. We do the calculation and we also compare some of them with experiments. After that, we try to apply this recurrent neural network to recognize the existence of OH and the CO groups. Now it seems we are able to do it very efficiently. With the infrared, we are able to recognize then the OH with 98% accuracy. With Raman, also 98. Another good thing is if we combine both, we can reach 99%. Yeah. So this is very reasonable, because when we try to measure a spectrum, it is learning of the reducing of the dimensionality. But if we are able to prepare different or various spectroscopic signal with several dimensions, then probably it's easier or maybe reasonable to reconstruct to retrieve their structure information. For example, here we move forward to this 2-dimensional spectrum. 2-dimensional spectrum is a cutting edge techniques which use like several laser pulses to treat one samples, then try to record the happening between different excitons. Then this 2-dimensional spectrum actually contain more information because it has higher dimensionality than the traditional 1-dimension like absorption spectrum or circular diode spectrum. So normally it contains more information, but also brings difficulties for theoreticists to understand them. Actually, during my postdoc study with Shaw Mugman in UC Irvine, like 10 years ago, I got a very painful days trying to do theoretical research to interpret this signal, yeah, which is a mess. Yeah. But now we realize that maybe machine learning is the right tool for that. Machine learning is good at treat this complicated signal, but also something with very, very solid rules behind that. Because we know some system has complicated data, but they don't have very solid rules Their rules are changing all the time, but in our physics words, the rule is always there. The photon response is all based on this understand the rule of quantum mechanics. Therefore, we now apply this neural network to do the discrimination for different second structure of protein. For example, if we use one-dimension UV absorption spectrum, we see it is not very bad to do the prediction with itself. But if we want to transfer to another protein or to very, very different the proteins, yeah, we get very bad results. This also the same system, same results with circular mechanism spectrum. But if we move forward to 2-dimension, we realize we can often always get good traceability and good prediction accuracy. Yeah. So this gives us this confidence. Maybe with, for example, if we combine 2D UV with other traditional spectroscopic signal, we may be able to improve our ability to reconstruct the molecular structure from spectrum. Yeah. Yeah. After that, I want to mention a little bit about another direction. We are now trying to use to make a correlation between spectrum and the chemical properties directly, not go back to the structure. Yeah. Why we want to do that? We see I have a lot of correlation with the experiments. When we try to collaborate with the experimentists, we start from structure. We do the quantum mechanics calculations, we have properties. And then we try to compare with experiments. Of course, we can compare the properties, but it's normally or always very, very difficult to compare the model structure with the experimental structure. First of all, it is very hard for experimentalists to identify their real structure in experiments. And the second, yeah, we know that our ability to do the simulation is limited. Yeah. Therefore, there's always a gap between the structure and then cause difficulties to reproduce the experimental properties. On the other hand, we can always do the quantum mechanics calculations to get a spectrum. And also we can do the experimental measurements to get a spectrum. Yeah. Then we realize actually it is easy to compare a spectrum with simulated results or compare the properties between study and experiments. Then why don't we just build a correlation between structure and spectrum and also structure and property? Yeah. Actually, this is quite straightforward. For example, in this work, we are able to predict the spectrum based on structure parameters. And in this work, we are able to predict the catalytic performance or catalytic property from their structure descriptors. Yeah. Then, if we are able to correlate these two and also structure and the spectrum, why don't we build the one-to-one correlation between spectrum and the property directly? After that, maybe in the future, if we have a transferable model, then maybe people only need to input the experimental spectrum to be able to predict the experimental properties. This maybe is a way for us to skip the huge difficulties to check or to identify the experimental structure. Anyway, even in the calculation, we know that somehow it's kind of difficulty to prepare the descriptors from the structure details, because you actually need to convert the complicated structure into several digital numbers. Yeah, there's always some tricky problem to convert a structure into numbers. But actually, spectroscopic signals, they are naturally numbers, and they naturally incorporate a lot of quantum mechanics information and also information from the environment. Therefore, we try to do it to demonstrate this idea in study. Yeah, firstly, yeah. So we do the DFT calculations. From structure, we get spectrum, and also from structure, we get this structure surface interactions between catalysts and also molecules. After that, we try to, if it is possible, to use the signal, the photon response signal, like infrared, to predict their properties. Now, since the results are quite good, we can predict the absorption energy. We can predict the charge transfer, the ability. We can even predict the d-band center. Yeah, we know d-band center are only defined in theory. It is somehow not possible to measure it in experiments. But suppose we have built this one-to-one correlationship between d-band center and the spectroscopic signal. Then maybe in the future, experimentalists can measure their spectrum response and then tell you how is the d-band center in this catalyst surface. Yeah. Also, we can do it with Raman. Raman can also do this same job. Yeah. Give us a good prediction. Yeah. To build the one-to-one correlationship between spectrum and properties. And this model seems to be able to transfer to another system. For example, we started with this pure silver surface or gold surface. Now we can transfer to like this high entropy alloy system. And we actually transfer to metal organic framework and also transfer to some metal oxide system. It seems their transferability are quite okay. You only need to input a small data set of this new system. Then you will be able to get a good prediction. Yeah. So maybe in the future, we'll try to get some experiment data, then build a model which can help us to explain the experimental results directly. Yeah. For the final remarks, yeah, I believe there are two ways to do the scientific research. One is like Heisenberg said, a theory is based on the directly observable magnitudes. And Einstein said, it is a theory which decides what we can observe. So it is from theory to get data or from data to extract theory. Maybe now, with the help of new tools, we can combine these two directions. Firstly, we can use quantum mechanics calculation to produce a lot of data. With this data, we know that they are solid because they are based on the basic rules. And then we can build a model. This model can be retrained, secondly, retrained by the experimental data, because the experimental data, it contains high complexity. It involves the environment and so on, many other interactions, but they're still based on the basic rules. Therefore, we believe that with the spectroscopy signals, they will provide us a good descriptors, because first of all, they can be measured, experiments, and they can be communicated, calculated. And also, the spectroscopic signal are interpretable, because all the descriptors, there are many descriptors, but I feel like it is not easy to interpret this man-made descriptor. But on the other hand, spectroscopic signal, they are the physical-based descriptor. We can interpret it from the basic equations. Yeah. Therefore, yeah, it is probably a way to combine the computation resource from the basic rule and also the very expensive experimental measurements, yeah, together using this second retraining of a theoretical based model. Yeah. So then we try to build the one-to-one relationship, and maybe in the future to apply then to different applications like materials reverse design and synthetic robots, and also interstellar chemistry measurements and so on. As a summary, we have developed this machine learning protocol, which enables us to accelerate the spectroscopic simulation, and also we're trying to push or to convince people to use spectroscopic descriptors for the machine learning study. Yeah, and let me thank a lot of people in our school, Professor Yilu, who has discussed a lot with me, and Professor Hao Ren from the University of Petroleum in China, and Professor Xiao Mukman in UC Irvine. Thank all of you for your attention.